All right. So today, I just handed back some homework as usual. I didn't print up a solution for you because, I mean, everybody's programs worked fine. So I didn't figure you needed a solution for this one. And now, the next big assignment, I don't know if you noticed, the assignment for Thursday is the complete project. So what you have to do next time is code generation. So I really am not sure if there's a whole lot that we need to go over to do code generation. I mean, you already have the main program set up to do the code generation and the listing, right? And so your listing one you can correct, and your parser, you can correct any of the errors that you had in your parser, so that should be fine. The only difference is now between generating code and generating the listing is you just generate some hexadecimal output in pairs of hex characters with one space in between. And the detailed specification is on the web. The only formatting requirement is that you have to be able to copy and paste your hex output to the object pane of the PEP8 assembler simulator and have it load and run. Now, in order to do that, you have to make sure that if you start a new line of hex code, that there are no trailing spaces. But there also has to be exactly one space in between pairs of hex characters. You know, and it has to terminate with the lowercase zz. All right? Actually, there are a few tips that I can give you. Two of the tips, or one of the tips, is on the website. You know how both your hex and your decimal constants have an attribute of an integer value? You remember that? Mm-hmm. Right. Well, there is a when you use that either the the print f or is it string f?
String.format.
String.format. You know, there is a percent specification, format specification for hex.
%x.
Oh, is that what it is? Mm-hmm. Good. And the way you get, but now see, one integer value always represents 16 bits, mm-hmm. which is 2 bytes. And so you have to print out the first byte, followed by a space, followed by the second byte in hex. And the way you get the first byte, one of them you divide by 256, the other one you mod by 256. That's how you get the high end and the low end. Are you with me? And you can use that format lookup. Now, I remember you guys said that last time you couldn't look up, or you had a hard time looking up the field width thing or something. There's a way to specify how many characters, how many hex characters get printed out.
Oh, the hex one wasn't the problem. It was the string.
It was the string. Oh, I see. But anyway, there's a way to do that. You can look. Yeah, you can. It's real. The fact that you're storing the fact that you are storing your integer and decimal constant attributes as an integer is really nice, because you're going to be able, with that one integer, you're going to be able to format your hex very well, very easily, quite easily. Oh, that's right. You actually formatted your hex things with the 0x in front of them anyway, didn't you?
For the parser.
Oh, yeah, for the parser. So, yeah. Oh, so you know that. You know how to do that. But anyway, so the trick is you divide by 256 or you mod by 256 to get the high order or the low order byte. And there's another trick.
Okay.
Now you are going to like, I think, the fact that I insisted that you have a separate enum for your addressing mode, right? Mm-hmm. If you go back and look at the example of the map, do you remember that we printed out the ordinal value
You told
Here, actually here, let's go back. Let's actually take a look at it. Where is my map? Okay, here's the map. Wait. Okay, look, here, let's take a look at this map demo, Java input-output slide. See, it says planet Mars is red, enumerated output P Mars, ordinal output what? 3. And we had some code. We showed the code of how you get that ordinal output. Do you remember how we did that? How it did that ordinal output?
Isn't it like dot ordinal?
Yeah, there is a. I frankly don't remember. I always have to look this stuff up.
You told us that we wouldn't remember it.
Yeah, but now you remembered it, and I was the one who forgot. So what is?
Planet dot
Oh, there it is. Ordinal. There is an ordinal function that gives you its ordinal value. Now watch this, you guys. Watch this. Suppose that you want to generate the code for, let's say you want to do, say, is load X one of the ones that you have to do?
No, LDA.
Oh, LDA, not load X? Oh, LD, I said load X. I meant LDX. I mean, surely you do LDX and LDA.
We do LDA,
I
but
think
not
it's
LDA.
just,
Oh, really? Just LDA? Oh. Well, that was kind of silly. I should have had you do LDA.
you're being nice.
Okay, suppose you say LDA this, let's say SF. Now you have to generate the code for this, right? Well, let's do this. Somebody look up on the inside front cover what the opcode is for LDA.
RA.
1100 R AAA. Right?
Oh, the R's gonna be.
R is going to be 0.
R is going to be 0, 1, but AAA is also going to be zeros or ones. Are you with me?
LDA, we know that R is going to
But you know LDA, well, you know LDA is going to be 1100.
be 0.
Another
We
0?
know that it's
We
A
know
and
the
not
register.
X.
Oh, A is going to be, oh, I see. Yeah. Well, we don't, oh, because we didn't do the X. I see. Right, so you know LDA is going to be 11000 AAA, right? Now look, you guys, do you see that if you could just get this to be one integer, then you could output the code for this exactly the same way that we just said that you could output your code for an integer value as 2 bytes. In other words, divided by 256 and mod by 256 and use the hex format. Are you with me? So all you have to do is get this in its integer format. And all you have to do is just calculate the integer for this, and then you can output it the same way you do any integer, high order and low order. But look how slick this is. Watch this. The way you get the integer representation for this is the following. What is 11000000? What integer value is this? 1, 2, 4, 8, 16, 32. It's 64 plus 128. So here, let's do this on the side. 64 plus 128. 8 plus 4 is 12. 6, 7, 8, 9. This is 192. Are you with me on that? And now, what about this AAA?
Correct.
Well, this AAA, well, if it's SF, what you can do is, if you listed your enumerated values of your addressing modes, all in order, according to that table,
Oh, it would be 0, 1,
what
2.
is 0, 1, 2? is all you have to do is take the ordinal value of this, add it to 192, and then
Output the hexadecimal.
and output it as hexadecimal, high order and the low order. Is that slick? Which means is all you need to do to generate any hex code for this, for anyone, is to do what? Is to have this value of it. And guess what a nice slick way to do that would be? No. I mean, what would be a nice slick way to look up what this value is for every one that you have to do? Oh, come on. Table lookup with a what? Java map. Are you with me? In fact, that's how we do it in the PEP 8 assembler simulator. We have maps all over the place. Just not Java. We wrote it in C++, but same idea. Yeah? Is that cool? Is that a nice tip?
Start working on this one soon.
Yeah. And then the other thing is, and because you have those dot commands, the dot commands are a little bit different, right, because you don't have mnemonics. But what about your, so the one thing about the dot command is you gotta be a little concerned about the dot block, because the number is how many bytes get generated. So that's going to require some kind of loop. Are you with me? You're going to have to loop through and however many it says to generate, and generate that many.
Super.
You just make the correct string for that. But I think that's about all the tips that I have. I think with this, if you get this idea, it should be pretty straightforward.
So you're saying we should load all of our identifiers into, we'll have a table.
Well, I mean, you could either do that, you could either table lookup or direct code. You could say if it's this, if it's this operand or switch, yeah. The switch would be direct code technique versus, I mean, it's the same, you always have those two options.
Okay.
But I think it's pretty slick. How that enumerated value works out. Now, see, isn't it great that you
Yeah.
took that time to? Now that was payoff time for you to have done it the way it should have been done. All right, instead of combining them all.
So much. If you had said that then,
I would have complained some. All right. Well, good. All right. Well, good deal. So, like I said before, what we're doing now is we're going in parallel. So there were some tips on generating some code. I'm sure you'll have questions maybe Thursday. Actually, what's today? Monday? Oh, today's just Monday. Oh, we got all kinds of time between, I mean, you got tomorrow and Thursday that you can ask questions. If you want to get started on that tonight, that'll be good. And so you could have questions tomorrow, and then you'll have another couple days, and then on Thursday you can have questions too, because it won't be due till midnight, as usual, because it's electronic submission. All right. So what we'll do is we will continue our practice then of doing things in parallel. And if there's no more questions about how to generate code, since we got started doing that, we will continue on how a compiler works by translating from C++ to PEP 8 assembly language. Now, last time we did this, we learned this move SP to accumulator instruction. What was that for?
For call by reference with local variables.
Call by reference with local variables, okay, which is what we have here. And
did.
Oh, MoveSpa?
I remembered move spot, but I couldn't
MoveSpa, remember what it did? Yeah. Well, I got confused because it was move, I didn't know if it was move spa or move spa. MoveSpa. Okay, so actually, the next thing we're going to do is we're going to see how Booleans are stored. Now, I don't think I even have a.
No demo?
I don't have a demo, or I don't think I even have an exercise for you to do Boolean types. So we'll just go over this kind of briefly. But by the way, what we're doing is, do you know what the rule is in both C and C++ for a Boolean? What is a Boolean type the same thing as? I mean, what type? It's actually, the Boolean type is actually compatible with two different types.
Const.
No. Oh, true. Well, no. Yeah, you were looking at the slide, but before you're looking at the slide.
Integer.
Oh.
Gazoon type.
What about a double? No, not a double, an int.
An int. Actually, it's Boolean. Yeah, the Boolean type in C and C++ is compatible with both an int, and it's also compatible with a pointer. Because pointers are addresses, and addresses are basically what? Ints. You remember how we could have how we could do pointer arithmetic? If you had an array and you added something to the pointer, you actually added. It was like adding to an integer.
It's like stack pointer.
Okay, and furthermore, in C, here you can say this. You could say int j, and then you could have your program down here, and you could say if j, blah, blah, blah. Check this out. You can say int j, and then you could have some stuff, and maybe j gets a value somewhere. And here you could say if j. Now, do you know how C or C++, both C and C++, and I think even Java, maybe not Java. I'm not sure about Java. Anyway, do you know how this works? When it's true and when it's false?
Carry bit.
No. J is an int. So do you know when this is true and when this is false?
Odd and even?
No. Oh, nice guess. Odd and even. That would be interesting. That would be interesting, but that's not quite right. That's not quite.
The negative status bit.
Oh, negative or positive? Oh, that's another good guess, because J could either be negative or positive, but that's not it either.
Zeros.
Now, what about 0? What do you think 0 is?
The status.
No. If the value of J as an int is what?
It's false.
Is 0, then it's false. But here's the way it works in C and C++. C and C++. The way it works is J equals 0 implies false. But it's not J equals 1 is true, because there's all other values that J could be. So what do you suppose it is?
Everything else is true.
Yeah, J is not equal to 0 implies true. That's how it would actually work. And you can write C code like this, and that's what it does. Now, it might give modern compilers now might give you warnings, because they say, but an int can be. And furthermore, not only that, what about this? You could say,
Nothing.
I was going to say, you could say something like this. My object star J, and boom, boom, boom. And then you could say if J, blah, blah, blah. So over here. So you could say, so now what is J? This time what is J?
Pointer to.
It's a pointer.
Which is an address.
Which is an address. But now what is the interpretation? C, because an integer is just, a pointer is an integer. So C and C++. So now what's the interpretation of this if statement? If J is what?
same thing? 0?
Yeah, 0, but what do we normally call it 0 when it's a pointer?
No.
Null. Null, if you look up, you know, if you look up in the C library, null is just defined to be 0. Yeah, if you look it up in the library, null is 0. So J equals null, that means false. And then J not equal to null, that implies true. And so you'll frequently see this. It's not as common now, but there's a lot of code out there where J is a pointer, and this is how you guard to make sure that it's not a null pointer reference. You say if the pointer is pointing to something, and then here you have the code that does J star gets whatever, or whatever gets J star plus whatever. You see what I'm saying? Mm-hmm. And this is how you actually test. Instead of saying if J is not equal to null. So sometimes old programmers, C++ programmers will just say if J, instead of saying if J is not equal to null. Some people say, it's better to document it if you say J not equal to null, because then J is a pointer and da-da-da. And here it's an integer. But you know, this is the way it was in the original C language. So over here on this slide, what we have is, just to make it specific, false does equate to 0, but then if we're going to have a true, then true could equate to anything but 0. But see, this equates to 1. Mm-hmm.
This is why in assembly language you never have to compare anything to 0. You can just branch.
Yeah, well, the comparison with 0 is the most common comparison there is.
Right, so you don't have to compare accumulator with 0 when you could just branch after loading the accumulator.
Yeah, but that doesn't have anything to do with the Boolean type. That's just the fact that usually when you do a load.
But if this were to be translated into...
Oh, you might be able to use this fact in a test. Yes, you could.
So if you translate into, like for example, if you put if J is not equal to null, it would be different in assembly language than if J. Right.
Well, you would be comparing, in assembly language, you do have to, when it translates to assembly language, it does have to compare this with 0, regardless of whether you say load and then compare with 0 or just load and then branch on 0. In both cases, mm-hmm. you are comparing it with 0 to see if it's false.
Okay.
I don't know if that answered your question or not.
It's all right.
It didn't, but we'll go ahead. Okay, so anyway, here is an example, figure 6.32 from the text, that has a Boolean function, a function that returns type Boolean, and the name of the function is inRange. And what it does is we have, I don't know, this is some kind of tax calculation or something maybe, or you know, see if you qualify for some kind of discount or something. So here we have const int lower equals 21 and const int upper equals 65. And then we have this bool inRange, int a, and it says if lower is less than or equal to a and a is less than or equal to upper, return true, else return false. Now, I guess I could have written this with the trinary operator, huh?
That'd be interesting.
But I mean, you know,
Translated?
it would be translated the same way. Right? We have to do a short circuit evaluation, right?
Mm-hmm.
So we could have said if. No, we could have said return lower less than or equal to a and a less than or equal to upper question mark, and then true colon false. Yeah, but I mean it actually would be the same code in assembly language. Okay. And then what the main program does is int age, cin age, if inRange age, cout qualified, else cout unqualified. All right? So I don't think I'll take the time to, you know, have us try to write all this stuff down. But, well, maybe we can sort of do it in our head. What is the, age is going to be a local in main. Here, let's at least do the runtime stack. So here, age will be here, right? And then the stack pointer will start off here, and then after it's here, we'll allocate and the stack pointer will be here. And then, so this is a stack frame for main, right? I think I got that right. Make sure I'm doing this right. And now what does runtime stack look like? Is it non-void?
It's Boolean.
So it's non-void.
So we return value?
Yeah, so we have ret val. Yeah? Then what else do we have?
Then we have A.
A, formal parameter A. Is that it?
And then we need
The return address.
And the return address.
And
Any locals?
Stack frame, no locals.
So that's the stack frame. All right. Good deal. And so when the SP is up here, what will be our A will be what? A will equate to 2, right? So let's see if we can just speak the code. Talk to the hand. Speak the code. So what will bool in range be? So A will equate, but we just said A would equate to what?
2.
2. And now what will we do? We'll and we already had the equates for the true and false, right? Remember?
Yeah.
Here's true equates to 1, false equates to 0.
So that's in.
Do we have to do that at the beginning?
Yeah, we have to do that at the beginning of the program.
Oh, okay.
Yeah, this is not built in. I mean, this is what the compiler would have to do
Write
this.
that.
Yeah. So then how would we do if lower is less than or equal to A and A is less than or equal to upper?
Load A.
So it would do load accumulator A, addressing mode,
Stack relative.
because it's called by?
Call by value.
Because it's called by value. Right. So load accumulator A, stack relative. No, sorry. Lower. Sorry. We want to do it in the order that we get it there. So load accumulator lower, addressing mode.
Direct.
Well, it's a global, but it's a constant.
No, but it's a constant. Hold it. Okay, maybe we should do it. Here, let's do it. Let's do a few lines. We'll just do a few lines. Okay, so so what did we say? Dot equate. What does dot equate? Yeah, true, false. Okay, so that'll be up there. It was A, right?
Well, we have the constant.
We have the globals. Constant, lower, constant, upper.
What?
On the code, at the top, in the global variables.
We have global
Constant,
variables.
lower.
Oh, we have constant. Oh, those globals. Yeah. I see. Oh, those are globals. I see. That's finally, I'm with you. All right. So what is it? Lower.
Lower, uppercase, all.
Okay, lower.
And that's dot equate 21.
Dot equate. 21. Upper.
Dot equate 65.
Dot equate 65. And now we're starting our.
Do the true and false have trace tags?
Yeah, no, they don't. So they're up here. I don't want to bother about
Says
right.
the branch domain.
And so is the branch domain. Okay, so
We
now
have A.
here's our function. What's the name of the function?
In range.
In range. In range, parentheses, what, int A? Okay. So in range, this is where we have to access A, right?
Yeah.
So what is that?
That's A
A
is dot equate.
dot equate 2, and that's a local with a trace tag.
And then we need a ret val.
Oh yes, and we need a ret val.
Is it ret val dot equate 4?
Yes. Ret val dot equate, yeah, okay, this is good that we're doing this. Okay,
And then load accumulator.
and now is our actual in range, right?
Actually, wait, we have some, no,
And now it's in range, right?
Because we don't have any lower, we don't have any local variables.
Now, we don't have any local variables, so there's no sub, all right?
So load.
Okay, so now let's do, I said we'll say the code, but now we'll write the code. Okay, so now,
Load accumulator,
load accumulator,
lower.
lower, now, this is where we were,
Immediate.
Immediate.
now we understand that it's immediate. Okay, and now, okay, and now what?
CPA,
Compare accumulator,
A,
A,
stack relative,
stack relative,
branch,
and now do we branch now?
Play branches.
Yeah, it's short circuit evaluation, and this is with an or, no, this is with an and, isn't it?
so only if it's true do you check the second
So,
So we branch if it's false.
one. You branch if it's false, which means it's branch is greater than. BRGT.
so branch if greater than, we don't have to check it anymore,
Right, so branch to else.
to else.
Oh, we should.
Now we have to do the other comparison,
Load
the short,
accumulator.
so load accumulator,
Upper,
upper,
immediate,
immediate,
compare accumulator.
compare accumulator,
Oh wait, we
Wait,
actually
why?
load accumulator A.
oh, because of the order that I have there?
A.
Okay, load accumulator A,
Stack relative.
stack relative, good.
Compare
Compare
accumulator
accum-
upper,
upper,
immediate,
immediate.
branch if greater than.
Now, why is it greater than? Because if it's
Because if it's false, again, you still skip to the else.
false, we still skip to the else, and if it's false, if it's greater than. So to the same else. So there's a short circuit
Only now do
evaluation.
we return true.
And now the question is, how do we return truths here? So now branch if greater than, so this is the
We load accumulator.
then part, right? So here's then. Here, if you want to get,
That's fine.
okay.
Load accumulator.
Okay, load accumulator,
True.
true,
Immediate.
immediate,
Store accumulator.
store accumulator,
Ret val. Stack relative. Now we do the else. Oh,
yes.
we should,
Wait, is this right?
Red
We need
0.
We need a red zero.
Does it say return right there?
Return true.
Okay, then if it says return right there, then we ret 0 right here.
That was the issue with my homework, was that the return wasn't right there.
No, I don't remember.
Anyway,
But you want to have the code in your listing be in the same order as the code in the C++.
right.
You always want to have that in terms of style. Okay, so let's just ... I mean, we see how to do this. Right?
Yeah.
Okay, so let's see if we got it right. Drum roll. Boom. Well, did we do our equates right for lower and upper?
We didn't.
And did we do for
No. A.
For A and
A and ret val? We didn't do it right? What?
Is this wrong?
I think.
Isn't red val? Okay, so.
How could we have gotten that wrong?
Well, that's saying
we
that
need
there's
a
no
return
return
address, right?
address.
How could that be wrong?
Booleans not have return addresses because we have the global trues and falses, or
No, we did the ret val. I mean, we got this returns.
it needs a return address.
But doesn't the call function push the return address? So is the stack pointer at A technically instead of?
No. It's, anytime it has, when we did the call,
Right.
when we did the call, it came up here. This is A is 2, and this, how could that be right? Surely this slide is not incorrect.
Error.
All right, let's do a demo. Are you ready for the demo? I wasn't going to do a demo today, but we'll do a demo.
Does the demo work?
Well, the demos better work. Maybe my slide's wrong.
Maybe we'll find out.
All right,
32.
so here we go. Okay, so here's our demo, and we will go to the help system and discover what in the world is going on. So here's figure 6.32. Here's the one, and here's the C++ program, and here is this, and what do we have here? Oh, look at this. Ret val equate 4 a dot equate 2. So this is actually correct. So if we copy this to the source, and heck, as long as we're doing this demo, let's go ahead and compile it. And here's our nice assembler listing. Okay, and it's just like we did it up on the board. And now let's start the debug and see if we can check out this great trace feature. So here we go. There we're allocating age, and we got it. We did deci, and so the age is 25. And here we store accumulator -4 sub SP. So there we have A, and there's a ret address, and sure enough, the stack is like we set it. And I see we discovered that the code is correct in the simulator with the help system. And actually, we just checked the errata sheet on the book, and the book had that error in the original one, but it is on the errata sheet. So I just need to change my slide. Slide was incorrect. But we can see how it works. Boom, 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 qualified. All right, end of demo.
11.
All right, so we just discovered that my slide was incorrect. The original book was incorrect. The errata is in the book, and I'll correct my slides for, this afternoon. Okay, and then did this part we didn't do the code for the main program, but you can see how this works, right? Now there are actually some interesting issues about how to manipulate Booleans when the interpretation is like this. Because how do you suppose you have two Boolean variables and you want to AND them. Or suppose you have two Boolean variables and you want to OR them. So if, the question is, how do you do that in assembly language? Like if one Boolean value is qualified and the other one is, I don't know, wealthy, say. So you have something that's, if you're qualified according to this criterion and you're wealthy, or you're, it's some bracket, and both of them, one is true and the other is false. How do you do AND? How do you do OR? You see what I mean? Then the question is, how do you do that in assembly language so that everything is consistent? And having it's related to how you interpret them. So there's issues involved there, but they're just interesting little details, and you can read about that in the book. All right? So we just go over that. We'll just go over that very briefly now. Okay, now we get to what I think is really interesting. Now, we have done this figure 6.33 shows all the addressing modes of the PEP8 computer. There's 8 of them. And furthermore, which ones have we learned so far? Immediate, direct, stack relative, deferred. So we've learned half of them. The ones that we haven't learned yet are indirect, which is going to be important with pointers. And now the last 3 all have an X in them, in the letter, for indexed. So what data structure that's built into C and C++ and all programming languages what data structure has an index?
Array.
It's an array. So always built into the hardware of a computer is the ability to access elements of an array. Every computer, every CPU that has ever been designed has is designed with the idea that arrays are going to be very common. And so you want to be able to index the elements of an array. So the first indexed addressing mode that we're going to learn is X. Indexed, the AAA field is 101. And now, let's take a look at this table. This is really interesting because all indexed addressing is what? How do you get the address of the operand? What do you do? you take the operand specifier and do what to it?
Add the index.
Add X, well now what is that X? That's the content of the index register, right? And then that's the address in memory of where you go to get it, right? Now does that look familiar? It looks very suspiciously like what other addressing mode?
Direct.
No, I don't think so.
Stack relative.
Yeah, it looks very suspiciously like stack relative. In fact, what is stack relative? You take the content of the what?
The stack pointer.
The stack pointer and add that to the operand specifier, right? So in both cases, you're taking the address of a register and you're adding it to the operand specifier, and that's the memory of where you go to get it. Now, why do you suppose in stack relative we have SP first and operand specifier second, whereas this is just a matter of style, because we know, you know with addition A plus B equals B plus A, right? So why do you suppose we have for indexed the operand specifier first and the index register second? Why do we have, you see, why do we flip the order like that? Why do you think that is?
Well, in the next one we have it in the right order, and then you just.
Well, yeah, the next one has all, yeah, that's interesting. Well, yeah, it's kind of in the middle there, the operand specifier. But why do you suppose it's written that way? I mean, it's written that way for, I mean, admittedly, this is just style, but why do you suppose it's written that way? There's a reason for it.
Do you load the operand specifier first? Whereas in the other case, you load the stack pointer first?
No, that's all done at the hardware level, and it would work either way if we specified it like this.
It's not alphabetical.
Oh, you're alphabetic. Yeah, that was a good try. Alphabetic order. By the way, did you know there's no such word as alphabetical?
That's right.
It's alphabetic. And did you know there's also no such word as backwards?
Backward.
It's backward. There is no plural backwards when you say backwards. And did you know that it's not different than? It's always what?
Different than.
No, it's different from. You should get used to doing that. That's a very common error. But you ask any English, what do you call it? Grammar editor, copy editor. I got reamed over the, I said, oh, that can't be right. And I looked at it, oh yeah, you're right. It's different from, not different than, and there's no such word as backwards, plural, it's always backward. And there's, what was the other one?
Alphabetical.
And there's no such word as alphabetical. It's alphabetic.
What do people say alphabetical order then?
It's alphabetic order is the correct way to say it.
Is it in the dictionary?
Well, I mean, I don't know if it's in the dictionary or not, but I know that every copy editor I've ever worked with. In fact, I've even had examples in the, I had an example in my I had a program that said backwards, and then it printed out backwards, and it was STD, and a copy, I said, I know that's in your program. He said, but that's incorrect grammar. I said, really? He said, well, we better make it correct. That's how I learned backward.
That's interesting.
Yeah. Anyway. And not only that, penultimate means what?
Oh, the second to the...
Second to last. Yeah.
And to penultimate. It's the second.
Oh, is that? I did not know that one.
I mean, that's how it is in Spanish anyway.
Oh, that's how it is in Spanish. I wonder what it is in English. I wonder if there's an English anti-penultimate. There is?
Possible. I mean, it's
Oh,
possible.
you don't know for sure.
Anti-penultimate?
Anti, like A-N-T.
Anti-penultimate. Oh, that would be great. Ooh, that's even better than penultimate. The next to the next. Are you going to check it out?
Yep.
Okay, we'll close on that. We've wasted so much time on English here. We might as well just close on anti-penultimate.
I feel like elementary school does you wrong then, because they're always like, oh, get in alphabetical order.
Yeah, they don't know. I think a lot of elementary school teachers don't realize that.
I highly doubt it.
Yeah, anti-penultimate.
Anti-penultimate is third from last.
It's a last but two in a series, third last.
Third last, yes. Oh, great. Oh, man, that's another great word. Yeah, this happens. We just got through with March Madness. The penultimate is the quarterfinal. So the anti-penultimate round would be the eight.
Eights.
You gotta write anti-penultimate
That was the
down.
thing.
Yeah. Good deal. Well, with that, we'll see you next time.
Whole lesson. last 5 minutes. Just like,
With that, we'll see you next time. With that.